Assalamualaikum warahmatullahi wabarakatuh. Hello, my name is Taqiyya Najla Syarif with student number 220682990. Today I'm going to presenting my final exam answer for numerical method class. From the previous video, I already explained for the number 1, so we're going to move on the question number 2. Okay, this is the question number 2. We're going to solve this with the framework called the E5. The first one is an intention. The aim is to determine the proper shocks for the suspension system of STDs to avoid damage to the satellite caused by severe terrain. We need to solve the associated non-homogeneous differential equation for the first model and analyze the displacement for each shock absorber. Additionally, we will determine the best shock absorber for the suspension system based on the performance and long-term effect on the satellite. Next, this is the initial thinking. To approach this problem, we have four. The first one is non-homogeneous equation solution, which means solve the differential equation for the spring mass damper system with the given force function for each shock. And then next, we have displacement analysis, which means find the maximum and minimum displacement for each shock and present this in a table. And the next, shock performance, which means analyze the long run performance for each shock and determine the best one for the suspension system. And then the last but not least, homogeneous equation solution, which means solve the homogeneous differential equation for the recommended shock, identify the transient and steady state solution, and analyze their effect on the satellite. Next is the idealization. We have model assumption and equation of motion. For model assumption, we have force on the shock is modeled by that and initial condition, and mass of the satellite and specification for each shock, spring constant K and damping coefficient beta. And for the equation of motion, we have the differential equation for the damped harmonic oscillator with an external force is that, and we will solve this equation for each shock and analyze the result. Okay, this is the instruction set. First thing first is solve the non-homogeneous equation. Okay, the differential equation is that, and we need to solve this equation for each shock absorber using the specific K and beta values. Okay, let's write the code to solve and plot this differential equation using Python's SciPy library. I already made the Pythons and that's on the slide. And this code will solve the non-homogeneous differential equation for each shock absorber and plot the displacement over time. Okay, for the step 2 is displacement analysis. We need to find the maximum and minimum displacement for each shock absorber. Okay, let's calculate these values and present them in table. This is the Python that I made. The result will show the maximum and minimum displacement for each shock. And then this is the step 3 is determine the best shock based on the displacement result and the performance. In the long run, we will determine the best shock absorber for the suspension system and explain the decision. And then last, the step 4 is homogeneous equation solution for recommended shock. Okay, let's assume that the best shock is extreme shock. This will be determined after analysis. We need to solve the homogeneous differential equation for extreme shock, identify the transient and steady state solution, and analyze their effect on the satellite. The homogeneous equation is mx plus beta x plus kx equals 0. Okay, let's write the code to solve the plot this solution. This is the Python that I made the code, and this code will solve the homogeneous differential equation for the recommended shock and plot the transient and steady state solution. Finally, we will discuss an effect of the transient solution on the satellite and why the chosen shock is the best option.